why Yeah. So to start off by setting a little context, there's been this sort of what I call great ML framework debate between what you can classify as eager mode machine learning frameworks and graph mode machine learning frameworks. And graph mode machine learning frameworks came first. There are things like TensorFlow and Cafe2 and others. And PyTorch, when it first started and just gained a lot of adoption, it was one of the first eager mode frameworks. And generally, eager mode frameworks are preferred by users. They're easier to understand and easier to debug because basically the way they work is, when you add two things together, you're actually adding the two things together, and you can print out the results. You can use a debugger. While in a graph mode framework, you're basically building, adding two things together is creating a node in a graph that you then need to execute later on, which adds this layer of indirection, which can be confusing for some users. PyTorch has primarily been a graph mode framework, but unfortunately, primarily been an eager mode framework. But graph mode frameworks have other advantages, and they're easier to optimize. And there's been this sort of constant conflict or constant debate between the two. And over the years, because of the advantages of graph mode frameworks, PyTorch has made many attempts at doing graph mode type things. So there was torch.jit.trace, which is basically like a record and replay system. The problem with this is it's unsound. There's torch.jit.script, which ahead of time parses using like AST parsing Python into a graph format. The problem with this is that it doesn't support all of Python, and so it only works in around half of real-world models, a little bit less than that. And then there was another attempt was lazy tensors, which is how TorchXLA used to work, which is graph capture through deferred execution. And the problem with this is it has high overheads and it has performance cliffs in cases where you need to synchronize. And what we learned from building all of these prior attempts at graph mode frameworks in PyTorch is PyTorch models aren't static graphs. Due to the history of PyTorch starting as an eager framework, PyTorch users have written models taking full advantage of all the features of Python. And so I think in looking at our sort of larger benchmark suites, around 80% of models can be converted into a single whole graph. But there's about 20% of models that do stuff like use Python types, use other third-party frameworks, have data-dependent control flow, which don't fit into these sort of graph mode frameworks. And so basically what we found is really like this graph mode abstraction doesn't fit what actual PyTorch programs do. And so the goal of PyTorch 2, which introduced torch.compile, was to get sort of best of both worlds, where we sort of see the space of different frameworks as this trade-off space, where on one axis you have usability, and PyTorch 1 was very usable, and that's why it got so much traction and adoption. And then there's lots of graph mode frameworks, and surprisingly, some of the graph mode frameworks are actually slower than PyTorch eager mode, but sort of all of them present this usability trade-off where they are harder to understand and often don't work on all PyTorch models. And so the goal of PyTorch 2 was to get the best of both worlds, be both fast and then also maintain the eager mode usability and programming model. So we introduced now a couple of years ago Torch compile. And the goal of Torch compile is you pass Torch compile your model, and your model goes faster. And we support all of Python, at least aspirationally. And so there's two pieces to Torch compile. There's Torch Dynamo, which is our front end and graph capture, and there's Torch Inductor, which is the back end. I'm first going to talk a little bit about Torch compile, or sorry, Torch Dynamo. So here's an example of a custom user-defined backend that uses Torch Dynamo. So this is sort of how you'd use the front end if you wanted to build your own compiler. So you can define a myCompiler function, which takes a graph, which is sort of a captured version of your program, and it takes a list of example inputs. This this sort of toy compiler just prints out the graph and then returns it unmodified. And then you have this, you can use the torch compile decorator. The torch compile decorator takes this optional backend argument, which in this case we're setting to this my compiler, which I've defined above. But there's actually now more than 20 different compiler backends for torch compile. And the default one, torch inductor, is what I'm going to talk about later. But here we just have a toy example. This toy example takes one of your inputs, it divides by the absolute value plus one, and then it does this dynamic control flow where it sums up the elements, and if the elements are positive, then it does one thing, and if the elements are negative, it does the other. And this control flow is tough for a lot of graph mode frameworks because a lot of the backends don't have great support for control flow. And so the way Torch Dynamo handles this is it does what we call a graph break. So if you run this program many times, what you'll end up seeing is 3 graphs get printed out. So there's one graph which represents everything up to the if statement, including the less than operation. And then we have one graph for when you take the true branch, and then a second graph for when you take the false graph. And so how does this work? And so basically what Torch Dynamo is doing is it's modifying the CPython interpreter using this hook called pep523. And what pep523 allows you to do is to replace the interpreter function that interprets a frame of Python bytecode. And so the default CPython behavior, when you call a function foo, you have a frame object which represents the dynamic call to foo. The frame object has a pointer to the code object, which includes the Python bytecode. And the default behavior of CPython is you have this function pyevalFrame default, and pyevalFrame default is going to step through this PyCode object one bytecode at a time and interpret it using a stack machine. And Torch Dynamo, on the other hand, you still start the same. You're still calling foo. You still have a code object, and you still have this dynamic frame object. But rather than interpreting the frame, what Torch Dynamo does is it symbolically evaluates it. So it's going to step bytecode by bytecode. And rather than actually executing the bytecodes, it's going to try to model their behavior. So and as it models the behavior, it tries to take the things it sees and put them into 2 buckets. And so there's a bucket of torch operations, which they're calling the fx, the torch.star bits, and it puts this in an fx graph, basically saying, well, if you call torch.add, Torch Dynamo knows what torch.add does, and so it's just going to add a node to the graph. And then if you do Python things, or if you do something like, suppose you call like a third-party C function in Python that Torch Dynamo has no visibility in, it's going to leave that in Python. So you end up getting some sort of residual Python bytecodes, which are put into a transformed PyCode object. And this transformed PyCode object is eventually going to call a compiled version of the captured FX graph. So we basically stripped out all the PyTorch operations from the Python bytecode, and we've compiled them with this user-defined compiler, and we've inserted a call that to represent them. And the invariant here is that the transformed PyCode object should have the same semantics as the original code object. And so this analysis is a dynamic analysis where we're dealing with like runtime types, and potentially the Python bytecode could load global variables, and those global variables could potentially change. And so as we're doing this analysis, we create what we call guards, and these guards are basically going to check invariance. So if your input is a tensor, then, well, if you change your input to an integer, then the semantics of the function are going to change. And so we insert a guard that says, okay, this input must be a tensor, and we'll guard on various properties of the tensor. And if you load a global function foo, and we inline the global function foo, then we need to insert a guard that the function foo hasn't changed. Because in theory, in Python, the user can overwrite foo and set foo equals to bar. And so we need to actually guard on that. And so what we do is we take all this stuff in sort of this write box, we cache it, and we check whether the cache is valid based on this sort of set of guards. And if the cache is valid, or if we've done this transformation, we then patch the PyFrame object to point to this new code, and then we actually just call the original PyEval frame default. So this allows us to support basically everything that Python does, or nearly everything. And allows us to seamlessly sort of go fall back and because this happens recursively, this process might happen multiple times. And sort of in the example previously, we get 3 graphs, and these 3 graphs would represent 3 sort of invocations of this write bit. So next, I'm gonna talk a little bit about Torch Inductor, which is our compiler backend for Torch compile. And so first off, let's start off with some design principles that sort of inspired the creation of Torch Inductor. The first is we wanted something that would be PyTorch native. So we want similar abstractions to eager PyTorch to support most PyTorch operations. Second, we wanted something Python first. And so we built our compiler in Python. And part of that was like looking at the contributions to PyTorch. What we see is that the parts of PyTorch which are implemented in Python get a huge amount of community contribution. We constantly see users of PyTorch going in and hacking on them and changing them. And that's one of the sort of the advantages of PyTorch, is how hackable it is. But in contrast, if you look at the C++ parts of PyTorch, it's a little bit more of a ghost town, where like fewer people contribute to them, fewer people are able to hack on them. They're much less accessible to users. And so we wanted something that was really easy to hack on. And so we went and embraced Python in a lot of our design decisions. Then finally, we wanted something breadth first, so something that would support a large number of PyTorch operations and can scale well. Then there's three technologies that it uses. So first, Torch Inductor uses a define by run loop level IR. And so this is, it actually directly uses Python lambdas in its IR, which I'll give an example of later. Next, dynamic shapes and strides are really important for PyTorch. So we use SymPy to reason about dynamic shapes and indexing. And Torch Inductor was built with dynamic shapes from the ground up. And next, we wanted to reuse state-of-the-art languages. So we generate output code in Triton for GPUs and C++/OpenMP for CPUs. We've actually recently added a Halide backend, which supports both of these. And we're in the process of building a MacBook Metal backend as well. So we'll have 4 backends total. So if you haven't seen it before, what's Triton? So the way to think about Triton is a higher level version of CUDA. And sort of the interesting thing about Triton is it exists in this sweet spot where it's higher level than CUDA, but then lower level than a lot of pre-existing DSLs, which allows non-experts to write fast custom kernels. And really before Torch Inductor, I was looking at a lot of these custom Triton kernels that users were writing, and I sort of decided like, oh, like we can cogen this, and that's sort of what led to the decision to use it. And it turns out that it's very very useful, and that it's easy to generate code for, but gives pretty good performance in a lot of scenarios. So here's an overview of how Torch Inductor works. So at the very beginning, you have AOT autograd, and AOT autograd is basically solving this problem of we need to support both forwards and backwards, and we need to support both forwards and backwards in this partial graph scenario where potentially we don't have everything ahead of time. So what AOT autograd does is it traces a joint graph. So we basically stub out everything that comes before and after the partial graph, and we trace through both the forwards and the backwards the graph fragment. This is going to give us a combined graph that does both the forwards and the backwards. We then run a partitioner to actually take that combined graph and then split it into two pieces. And we use a min-cut algorithm to try to minimize the memory we need to save from the forwards to the backwards. Simultaneously, while we do this, we also run functionalization to basically remove mutation from the graph to make our compilation job easier. And we also run decompositions, and these decompositions basically turn sort of the around 2,000 operators in PyTorch into around 200, because we basically take the majority of the operators and we break them into smaller pieces, which are easier to reason about. Next, we have the graph lowerings. So the graph lowerings are converting from the FX graph that Torch Dynamo captured to a loop level IR. And so the original FX graph is operating on tensors of elements where you're dealing with an entire tensor at a time. We lower that to an element-wise representation where we're operating on scalars. Next, we have scheduling. So during scheduling, we do horizontal and vertical fusion decisions. We do tiling. We do memory planning. And we auto-tune some kernel selections as well. And finally, on the output code, we generate two pieces of output code. So we do the backend code gen, which either Trident C++ or Halide. And we have our wrapper code gen. And the wrapper code gen basically replaces the interpreter. It's what calls the kernels that we generate. Okay, so let's run through an example. So here's some sort of a toy example that I've given, and this toy example takes an input. It calls sine sine, then cosine, then returns to the both of the values. And I've gotten most of the stuff I'm going to show in the next slides by running with this torch compile debug flag enabled. And so first we get this FX graph, and since I'm only showing the inference case here, we end up seeing sort of these same two ops, sine and cosine, but these two ops have been normalized down to actually call like the specific overload that they're needed. And so some operations have like overloads for like integers versus tensors or various different argument combinations. So we've resolved the specific overload. We've normalized all the operators to a specific form. And if you were using sort of a more compound operator, like if you had like a layer norm in here, we would have turned that layer norm into basic like add sum operation. So we would have decomposed it into a simpler form. And if we were doing training, we'd have the backwards version of these operations as well. And so, the derivative of a sine is a cosine, and the derivative of a cosine is a sine. And so you end up having four operations if this were training. So next we have the define by run IR. And so the define by run IR actually will generate Python functions in the form of closures that represent the bodies of loops. And so we have here on the right, these are sort of the IR nodes. So you end up having a few wrappers to model mutation. And then you have this computed buffer IR thing, which is given a name. It has a layout, which basically says, okay, how's the memory organized? And then it has this pointwise operation. This pointwise operation has a range, basically the iteration range, and then a pointer to one of these two functions. And each of these functions sort of represent the element-wise IR that Torch Inductor uses. And we see here what this IR does is it unpacks the index here. It calls the operator load, which takes the name of the input buffer, and then it actually has the memory indexing formula. So in this case, we've taken the two-dimensional indexing and we've turned it into just an address calculation in the IR. And then we have the operator, and the difference between this operator and the previous one is this one is just operating on a single element. So next up, we have scheduling and fusion. So scheduling and fusion is what is where we actually take these things and combine them together. So this is the graph that's going into our algorithm where we have the input, we have our two operations, and then we have the output, which includes both operations. And there are sort of two key functions in the scheduler that control fusion. We have this can-fuse function, which basically is like a legality check, like, okay, is it semantically correct to fuse these two things? And there's also some heuristics in there because there's some fusions which are unprofitable, which we want to avoid. And then there's the score fusion function, and the score fusion function basically controls what order we do the fusions in, because there can be cases where two fusions are mutually exclusive. Like if I fuse these two things, then I'm going to create a dependency edge which prevents me from fusing these two other things. And so we basically just do a greedy algorithm for fusions where we rank all the fusions that are possible using the score fusion functions, and we just iterate through that list, and we need to recheck that they're still legal, and if they are still legal, we can do the fusions. And so all this turns out into some output Triton code, and so this is what the generated Triton code looks like. Here we have a pretty standard Triton function, which does both the sine and the cosine operation, and then does two writes, because we need to return two output buffers for this code. And if you haven't seen Triton before, Triton basically operates on blocks. And so in this case, we're computing X block elements at once, where X block is something like 1024. And what we do is we compute, we do a range. So we're going to take like 1024 contiguous elements of the tensor. We need to, it may not be a multiple of 1024, the total number of elements. So we need to do a mask to basically mask off any elements that are extra. And here you can see we then load a block of 1024 elements at a time, and then do the necessary operations on that block of elements. So similarly, or I guess that's not similarly, the wrapper code that calls this it looks like this. And so here the wrapper code is doing some size computation at the beginning. It's allocating the two outputs using symbolic shapes. And then it's invoking the Triton kernel I showed on the last slide. And for contrast, if you instead move your tensors to into C++, the output code would look like this. So here, this is basically a C++ output where we have an open MP4 loop. So this is the pragma OMP4. And here we do vectorize 16 elements at a time using the same vectorization classes that C++ PyTorch uses. And then there's a tail loop to handle any stragglers at the end. So here's performance across our benchmark suite. So we have three benchmark suites that we measure on. We have TorchBench, which at the time was 57 models, but has since grown. We have Hugging Face, which is mostly transformer models, and we have TIM, which is mostly vision models. And here we're comparing to 6 other compilers. So we have, and this is speed up over PyTorch eager mode. So higher is better. And and 1x means you're running the same speed as PyTorch eager. So we can see that across all 3 benchmark suites, Torch Inductor is providing inference speedups, between 1.9 and in the high 2x range, and similarly, we're also providing speedups for training, and these speedups are exceeding the other compilers that we tested, and these are geomean speedups on float 16. And here's an example showing the distribution of speedups. And so the way this works is we have the different amount of speedups, so up to a 10x speedup, and then the count of how many models achieve this speedup. And this is the a cumulative distribution. So here like this point here means that we have around 40 models that provide a greater than 4x speed up. Around 50 models that provide greater than a 3x speed up. And you can see sort of how there's a long tail of models that get a pretty large speed up with torch inductor. While for some of the other compilers, a lot of the speed ups are sort of clustered more around 1x, and some compilers generate a lot of slowdowns, which pull down their averages. Then here's a a a breakdown of where these speedups come from. So this is an ablation study where we basically take torch inductor, we remove one optimization at a time. Sorry. Where if you do all optimizations, we're getting an inference speed up of 1.91x. And if you take away loop layout reordering, it doesn't change at all. If you take away the matmul templates, it goes down to 1.885x. And the idea here is that if taking away an optimization reduces the speed up substantially, then that optimization must have been important. And so this sort of tells you that by far the two most important optimizations are fusion and inlining. Fusion and inlining are a little bit related. They're both ways of combining two things into a single kernel. And so if you disable both of them, torch inductor actually generates a slowdown. And so this tells you that the decompositions we're doing during AOT autograd, in order to just get back to baseline performance, we have to do some fusions to combine them together. And so they were primarily coming from these general fusions. And so in the interest of time, I'm actually going to skip this last section talking about halide and hopefully take some questions from the audience. So you guys are muted.
Yeah, sorry about that. Well, thank you. Thank you for the lecture. Does anybody have any questions? Yes.
So given that the compute graph with a custom CUDA matmul kernel, for instance,